Now, in our last class, am I audible to all of you? Hello? Okay. Now, in our last class, what we have to
Yes,
study,
ma'am.
we have studied three different types of ADCs. First one will be the counter type, next one successive approximation type, and the last one is the dual slope integration type of ADC. Though we have a single slope also, but we use dual slope because we have found that the dual slope has certain advantages over single slope ADC. So we go for a dual slope, and among the ADCs we have studied, the dual slope A to D converter is commercially used because it is less costlier than that of the counter type and successive approximation type ADCs. And why those ADCs have higher cost? Because they have inherent DAC within it. Where I have seen in dual slope integration type, don't need an ADC. We simply need an integrator and a counter. And then we have find out the quantization error, and we have seen if we have a truncation type of ADC, then the quantization error will be equals to Q, which is equivalent to quantization step. And by using rounding off type ADC, we can reduce the quantization error within plus minus Q by 2, where Q is the quantization step, and quantization step is equivalent to what? Hello? Quantization step is equivalent to what?
One
Hello?
LSB.
Yes, it is 1 LSB or VFS by or VREF by twice N, where N is the number of bits in a converter and VREF or VFS is the full scale voltage. So in rounding off type ADC, we have seen we can reduce the quantization error from Q to plus minus Q by 2, which is plus minus half LSB. This will be the quantization error for truncation type of ADC, where output changes state at the end of quantization step. And in case of rounding off type ADC, this is an input-output relationship of the rounding off type ADC. Here also the quantization step output changes state at the end of quantization step, which is equivalent to Q or 1 LSB. But in case of 000 to 001, it is 0.5 LSB, and from 110 to 111, it will be quantization step will be 1.5 LSB. So in case of rounding of type ADC, the output changes state at the end of quantization step, except first and last step. For the first step, the quantization step will be 0.5 LSB or Q by 2, and for the last step, which is from 110 to 111, it is 1.5 LSB. And with the help of this, we can limited our quantization error within plus minus half LSB. And this quantization error can again be minimized if we are increasing the number of bits or the resolution. Because if the number of bits will increase, say if it is 3 bit, then it will be VREF by 2 to the power n, and where n is 3, And if we, in that case, if we take Vref to be 8 volt, and then the quantization step will be what? What will be the quantization step for VFS 8 volt and N equals to 3 bit? Hello?
1.
1. And now if we increase the number of bits, say instead of make it 3, we make it 4, then it will be what? If we have a 4 bit, and Vref will remain same, and we are increasing the number of bits.
It will be, ma'am, it will be
0.5 volt. Yes, 0.5 volts. So the quantization step will be smaller. Now ADC resolution, just like in case of DAC, it will be 1 by 2 to the power n, or in terms of voltage, it will be FSR by twice B, 2 to the power B, capital B, where B is the number of bits, and FSR is the full scale range of the ADC. And in percentage, if we multiply this by 100, then we get percentage resolution. Now we come to the ADC errors. In DAC also we have offset error, gain error, and linearity error. The same errors are in case of ADC, but here the way of expressing the error is different. In case of an offset error, it will be the horizontal transition of the input-output relationship. Here, the ADC with offset error, the pink one will be an ideal ADC with quantization but without offset. And this is an input-output relationship. Pink one will be the input-output relationship of the 3-bit rounding off type ADC. And we know the in 3-bit rounding off type ADC, we have a quantization error within plus minus half LSB. So this will be the pink one, will be the input-output relationship of an ideal ADC without offset error. And the blue one will be the input-output relationship of 3-bit, again 3-bit rounding off type ADC with quantization, but with offset. And this, so here the offset error will be the horizontal transition of the input-output relationship curve. And this offset error is due to the, because in successive approximation type, as well as in counter type, in dual slope type, this will be the offset voltage of the op-amp used in the ADC. Or if there is a amplifier and comparator input offset voltages, and it is the horizontal transition of the graph for input-output relation. Now from this, the ADC with offset error, this curve is visible to you. Hello?
Yes, ma'am.
Now, can you tell me what will be the offset error in terms of LSB for this?
1.5.
Yes, how is it 1.5?
Ma'am, it will be from 0.5 to 2. Thus, we can calculate this.
Yes, because in if it is and without offset, then the transition from 000 to 001, it will occur at 0.5 LSB. But actually what we get, the transition from 000 to 001, it occurs at 2 LSB. So 2 minus 0.5, it is 1.5 LSB. or it will be ideal minus actual. Ideal will be 0.5 LSB, and we are defining offset error will be ideal minus actual. In ideal case, it will be 000 to 001 transition occurs at 0.5 LSB. But in actual case, where there is an offset error, the 000 to 001 transition occurs at 2 LSB. So the difference will be minus 1.5 LSB. Now in the next curve, here what will be the offset error?
Will be only 1 LSB.
It will be, let me, yes, 1 LSB. Now why it is 1 LSB?
0.5 to 1.5.
No, from 001 transition to 010 transition, the actual one will be, it is 1 LSB, because we know of in an ideal input-output relationship of 3-bit rounding off type ADC, the quantization step will be 1 LSB. So here, in actual case, it occurs at 1 LSB, but in case of, sorry, ideal, this is actual, red one, actually it occurs at, if we take 001 to 010, in case of actual, it occurs at 1 LSB, and in case of actual, it occurs at 0.5 LSB.
Yes, ma'am. In case of ideal, it will be 1.5.
Let me check. This is 1.8. So it is 0.5 LSB. Ideal, and from ideal, this will be 1.5 LSB, but in case of, I am talking about 001 to 010, but in actual it occurs at 00001 to 010. For an ideal case, it occurs at 1.5 LSB. And in case of an actual, it occurs at 0.5 LSB. Clear? This from 001 to
Yes,
010. This will be 0.5 LSB, and for the black one, which is ideal, this is 1.5 LSB. So it will be plus 1 LSB. And what we see the difference, can you see the, look carefully this graph and the previous one? This will be the, here, we have a negative offset error, and here we have a positive offset error. So how could we distinguish these two graphs?
When আইডিয়ালটা যখন অ্যাকচুয়ালি নিচে থাকবে তখন ওটা মানে যে পজিটিভ হবে, আর যখন উপরে থাকবে তখন ওটা নেগেটিভ হবে।
Yeah, that is the one way to describe it. But here, in case of offset error, which have a positive offset error, here the last transition occurs prior to the, it will reach the 7/8 VREF. Because here, last transition, that means 110 to 111, this occurs at 5.5 LSB, whereas it should occur in 6.5 LSB. So the output saturates prior, it will reach the full scale output of the ideal A to D converter. Clear? Because in case of ideal case, it will occur at 6.5 LSB, 110 to 111 transition. But what happens if we have a positive offset error? The 110 to 111 transition occurs at 5.5 LSB. That means the output will reach, that means digital output will reach when the analog voltage will not reach its actual value, which is 6.5 LSB. Clear?
Yes, ma'am. Yes.
Yes, ma'am.
And what about here? When we have a negative offset error,
Actual one actually reached there in 8 is at 6.5 and
here the output will remain zero. That means the digital output will remain zero for a large range of analog input voltage, because here up to this VREF, the output count will be, or the digital output will remain zero. Or the digital output will not change in state for certain values of, or values which is more than that of the ADC with a negative offset error. Because for this range of analog input voltage, we will get the digital output to be zero. Clear?
Yes, ma'am.
yes, ma'am. Yes.
Because for this range of analog input voltage, the output will be zero, whereas the output will remain zero for this amount of voltage, analog input voltage. But here we have this much of voltage as an input, up to this much of voltage as an input, the output will be zero. Now the gain error, it will be again the change in slope of the input-output relationship, just like in case of DAC. And here what we know, the in output digital word, this is n, which can be written as ai to the power minus I, sorry, a1 to the power minus 1 to a2 to the power minus 2 up to an to the power minus n. That will be the equals to the digital word, or this is the sum of the digital inputs values, and it is V in by VREF. This we have found from the input-output equation of an ADC. Now here, V in is the unknown analog voltage whose digital equivalent we are going to find out. So the here the gain will be 1 by VREF or 1 by VREF by VFS. Now if the reference voltage changes or the full scale voltage changes, then the slope will also change, and this again be this slope 1 by VREF can be represented as 1 by alpha VREF. So 1 by alpha, and alpha is a positive coefficient which is equals to 1 in absence of gain error, and which is less than or greater than 1 in presence of gain error. Now if alpha greater than 1, then the slope will increase or the slope will decrease.
Decrease.
And if alpha less than 1, then slope will increase. And this is due to the gain error, because in case of ADC, we have a DAC, and the DAC is made up of a resistor network. If the resistor values of the network changes, then the gain also changes, because in case of an ADC, we are going to find out the digital equivalent by comparing it with the DAC output voltage. And the DAC output voltage, if the resistor values are not accurate, the DAC output voltage will change. So due to that, there will be a gain error. And therefore, alpha greater than 1, there will be a decrease in slope, and alpha less than 1, there will be an increase in slope. Now here from the graph, what we have seen, the pink one will be the ideal input-output relationship of a 3-bit rounding off type ADC, because all the ADCs we are going to use, whether it is a counter type or a successive approximation type or dual slope type, they are all rounding off type ADC. So I am not going to repeat rounding off type ADC again and again. All the ADCs we are using both commercial and non-commercial ADCs. They are rounding off type ADC to reduce the quantization error. Now here from the graph of the gain error of ADC, what we have seen, if alpha less than 1, then what will be the graph, and when alpha greater than 1, why the graph will looks like this? Do you have any idea?
ম্যাম স্লোপটা তো বেড়ে গেছে, মানে যে আলফা গ্রেটার দেন 1 হলে তো ওটা 1/alpha vref যদি ধরি, তো এটা 1/2 ইন্টু VRF হচ্ছে এই আলফা যে গ্রেটার দেন 1 হলে। আর ওপরের যদি যে আলফা লেস দেন 1 হয়, তো ওটার জন্য 1/0.5 ইন্টু VRF হচ্ছে। তো আলফা লেস দেন 1 হওয়ার জন্য ওভারঅল যে স্লোপটা যে বেড়ে যাচ্ছে, মানে আলফা ভ্যালুটা লেস দেন 1।
Yes, in terms of quantization step, what we could say, if alpha less than 1, the quantization step will be smaller, and the output will reach the final value before we complete the full scale analog output voltage, because here the output will reach its highest value, which is equivalent to 111 at this point of analog input voltage. Whereas if the slope is greater than 1, then the quantization step will be bigger, so the output will never reach its state 111. Clear? If the quantization step will be smaller, so the output will reach much faster than that of when the quantization step will be higher. Clear?
Yes, ma'am.
Yes, ma'am, clear.
Because here the quantization step is smaller in every case, and here the quantization step will be like this when alpha greater than 1. Slope is decreasing. And how to measure gain error? Now in rounding off type, we call it an ideal ADC, where and quantization error is inherent in ADC, whether it is ideal or non-ideal. The quantization error will be inherent in ADC. That we have already know. Now, in case of a rounding off type ADC where quantization error is present, we know the first transition voltage, that means 000 to 001 occurs at 0.5 LSB, and I have already told you the last transition, that means 110 to 111, it will occur VFS minus 1.5 LSB. Because here, this is VREF or VFS. So this will occur VFS minus this at this pointer, or this will be 6.5 LSB. 6.5 volt equivalent to that.
Yes, ma'am. Yes, ma'am.
So it will be VFS minus 1.5 LSB. So the difference between these two will be the first transition, last transition, and first transition. It is VFS minus twice LSB. This is for ideal ADC. But in case of an actual ADC, it will be the gain error is, how could we find that? Ideal difference between last and first transition and measured difference between last and first transition voltage. FSR minus twice LSB or VFS minus twice LSB minus measured difference between last and first transition voltages. And since it depends upon VFS, so it will either express in terms of LSB or percentage of VFS, because it again depends upon the value VFS. What we have seen earlier, that N will be Vn by Vref or VFS or FSR. Now come to the linearity error. This will be the change in code width of the different transition voltages. Now how could we define code widths? Now code widths in terms of quantization step or code width, we can define the range of analog input voltage for which the digital output occurs. Now, we know the nominal value of the code width is the voltage equivalent to 1 LSB, except first and last code, because the first code width or the quantization step, what we know, it is 0.5 LSB, and last quantization step, it is 1.5 LSB, and except these two, the quantization step is 1 LSB, just like here. In gain error, since this is the ideal input-output relationship, so the first transition occur at 0.5 LSB, and after that, this is equivalent to quantization step or 1 LSB, except last transition, where 110 to 111, it will be 1.5 LSB. That means and this is the code width for the last transition, which is from 110 to 111, is the voltage equivalent 1.5 LSB. Because during this interval of analog voltage, from here to here, the output code will be always 111. So this is so the code width is clear to you. What will be, how could we define code width?
Yes, ma'am.
It is the range of analog input voltage for which the given output code occurs. So here, from here, what we have seen, up to 000, up to 0.5 LSB, the output code will be 000. And for this range of analog input voltage, the output code width for the last transition will be 1.5 LSB and code width for the first transition is 0.5 LSB. And this ADC is an ideal ADC. Except these two, the code width will be always equivalent to 1 LSB or quantization step, because quantization step is Vref by 2 to the power n, where n is the number of bits. Now, if there is a variation in the code width, then the ADC has an error, and this error is known as linearity error. And this linearity, just like that, we have a differential nonlinearity and a integral nonlinearity. Now, differential nonlinearity will be actual code width minus ideal code width. Now see the graph. The graph is visible to you. Hello?
Yes, ma'am. Yes, ma'am. Visible.
Now tell me why from 001 to 010 the DNL is 0.2.
Madam,
For 000 to 001, the DNL will be 0 because both the transition occurs at 0.5 LSB.
ম্যাম একটা 0.5 থেকে 1.3 LSB পর্যন্ত হচ্ছে, আর আরেকটা 0.5 থেকে 1.5 অবধি হচ্ছে। ওই জন্য ওই দুটোর মধ্যে যে ডিফারেন্সটা ম্যাডাম 0.2।
Yes, and for the in the next step, why here in from 010 to 011 the linearity error, differential linearity will be 0.
ওটা 1 পয়েন্ট, এক মিনিট, 1.3 থেকে ওটা কত দূর বুঝতে পারছি না।
Now here, since here for the blue one, which is the ideal one, the quantization step will be equivalent to 1 LSB, and for the pink one, which is the actual, it is also 1 LSB. Though
Yes,
previous step, it has an error of 2.2 LSB, which is the actual code width minus ideal code width. But here, since both of them are 1 LSB, so this much, this will be equivalent to the red, the pink width will be at 010, it will be 1 LSB, and the blue one will be also 1 LSB. So the differential nonlinearity will be 0. Now, if the different code width, if the variation in the code width is such that, or the quantization step, if such a bigger amount, we will miss the code. See here from 011 to it comes to 101. Here the quantization step, it will be equivalent to, this is 1 LSB, this is 1 LSB, equivalent to 2.2 LSB for the actual case.
Yes,
And
ma'am.
ideal will be 1 LSB. Now, since the code width or the quantization step increases, we will miss the code 100. Clear?
Yes, ma'am.
This is due to the variation in the code width. But here the variation is such that we have missed the code. up to point plus minus 0.5 LSB, we couldn't miss the code. If the error is more than that, then we will get a missing code from A to D converter, and this is due to the non-linearity in the resistor values used in ADC, and ADC has a DAC, so it is the non-linearity of the resistor values upon which the DAC is being made. And so the differential non-linearity is clear to all of you. Hello? Only
Yes, ma'am.
one or two will give
Yes,
me
ma'am.
the answer. What about others? Why they are not responding? They are not listening? It is not possible for me to see that whether they are listening or not. Hello? 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 Hello?
Yes, ma'am.
Yes, ma'am.
Why
Yes,
are
ma'am.
you not responding? Now the integral nonlinearity, it will be again the summation of the differential nonlinearity. So here pink one will be the ideal transition and blue one will be the actual transition. So here this will be from 0, 0, 0 to 0, 0, 1. There will be no differential linearity error. But from 0, 0, 1 to 0, 1, 0, here it will be a 1 LSB, but in case of an actual, it will be 1.5 LSB. This one, pink one. So the integral previous from 0, 0, 0 to 0, 0, 1, it is 0, and from 0, 0, 1 to 0, 1, 0, it is 1.5. So 1 minus 1.5 will be minus 0.5 LSB. Here the integral nonlinearity error will be minus 0.5 LSB at up to 0, 1, 0. Clear? Hello?
Yes.
Yes, ma'am. Clear.
Yes, ma'am.
Now, I have told you if we have a voltage changes with time, so if in that case, the ADC will not convert the actual digital equivalent of the analog in. So we need a sample and hold amplifier. Now, sample and hold amplifier, it will works in two modes. One is in sample mode and another is in hold mode, and it actually consists of a capacitor and a switch. Now when the switch is being closed, then the capacitor will charge up with the voltage which is equivalent to V in, and when the switch remain open, then the capacitor has a capability of holding the charge and it will hold that voltage. And here we are using a buffer or unity gain amplifier at the beginning and at the at the input side and the output side of the sampling and hold amplifier. This is for We know this for unity gain amplifier has high input impedance and low output impedance. So the sample and hold amplifier, it works in two modes, sample mode and in hold mode. In sample mode, the capacitor is charged up with the input analog voltage, and when the switch is being closed and when the switch is open, since the capacitor has a property of holding the charge, it will holds the voltage, that voltage, until the switch is again closed. So these two modes are known as sample mode and hold mode. Say this will be the analog input voltage. Say here the analog, this is the sample mode at this instant, and this will be the, or this will be the sampling time, and this will be the holding time. So when their input analog voltage is of this much, then the output will be also equivalent to V in, or which is V out. Here this will be the output, and when the switch is being opened, then the output V out will hold that amount of voltage until the next sampling instant. So the output has a stepped waveform. So the output will be like a stepped waveform, which represents, or whose contour represents the V in. And we have two parameters here, acquisition time and aperture time. Acquisition time is the time required by the capacitor to get the charge of the input voltage applied to the sample and hold circuit. And aperture time, the time taken by the switch to change from sample mode to hold mode. So how could we convert a complete analog voltage into its digital form? We need to sample the input analog voltage, then we have to quantize it. How could we do the quantization? This can be done by the A to D converter, and the A to D converter output, and then we do encoding. Encoding means how could we represent the digital input in the form of an analog signal. This is known as encoding. So the analog voltage is completely transformed into a digital voltage by using three steps: sampling and holding. This can be performed by sample and hold amplifier, quantizing and encoding. Say here, oh sorry, I didn't show the graph here. So in quantizing we are going to, so this will be the analog voltage V out, which has a stepped waveform, and this stepped waveform is converted into a digital equivalent by using A to D converter, and then we are going to represent in encoding scheme. We are, how could we represent 0 1 0 0 1 0 1 0 1 1 1 and so on. This will be the in terms of digital signal, which has only two levels, either 0 or 1. That is known as encoding. So encoding is the digital word using suitable binary code. So this is all about analog to digital converter. Now we go for So this is the, we are going to start our next topic, which is cathode ray oscilloscope. Hello? Are you listening?
Yes, ma'am.
Now, oscilloscope, it is an electronic device which is used to measure wide variety of signals, whether it is an AC signal, whether it is a DC signal, whether it is an AC-DC superposed signal. And oscilloscope gives us amplitude versus time curve of a signal. Now, how the oscilloscope display a signal, this can be shown by when we are going to study this diagram. Now here what we have seen, we have a vertical amplifier and delay line. This block is known as vertical deflection subsystem, because since oscilloscope is used to measure or display wide variety of signal, so it consists of several parts, and for main thing of the oscilloscope is a cathode ray tube. Then we have a vertical deflection subsystem, which consists of vertical amplifier and a delay line. And next we have a horizontal deflection subsystem, which consists of a trigger circuit, time-based generator, and horizontal amplifier. And we have to use this is an oscilloscope probe, and this is a signal transmission cable. Now, when we want to display any signal in the oscilloscope screen, then what we do, we first sense the input signal at the source by using this oscilloscope probe. Now, when we sense the signal, it goes through the signal transmission cable, and it is applied to the vertical input terminal of the oscilloscope, and then we have a vertical deflection system, or it will connect to then signal is being connected with the help of the probe to the oscilloscope vertical input terminal. Now, often when the signal is presented at the vertical input terminal of the oscilloscope, which is marked in this diagram, in block diagram of a CRO as an input signal, the amplitude of the signal is sometimes low or sometimes high. If it is low, we have to amplify the signal to activate the oscilloscope deflection system, which consists of here vertical deflection plates and horizontal deflecting plates. These two deflecting plates we need to have, and these are kept inside the cathode ray tube. And sometimes the signal amplitude presented at the vertical input terminal of the oscilloscope is such that it will exceed the screen, or it will be beyond the oscilloscope screen. So to amplify the signal as well as to attenuate the signal, so that it will remain within the scope screen, we need vertical amplifier, and this vertical amplifier is consist of an attenuator and an amplifier. We will study in detail this vertical deflection system. Now, after passing through delay line, the input signal comes to the vertical deflecting or vertical deflection plates from the figure we have seen. Now, the horizontal deflection system or subsystem, part of the amplified vertical signal is applied to the horizontal deflection subsystem, and it consists of a triggered circuit, time-based generator, and horizontal amplifier. So this part of the vertical input signal, after being amplified, it is applied to the trigger circuit, and the trigger circuit is used to activate the time-based generator, and the output of the time-based generator which produce a sweep waveform, so that the voltage, the screen with the spot produced by the electron gun on the screen, horizontal movement of this spot across the screen, we need a time-based generator. Therefore, since the time-based generator voltage will move the spot of the light on the screen horizontally across the screen, so the time-based generator output voltage is proportional to what? Can you able to tell me? Hello? Hello? From the figure, what we have seen, the time-based generator output voltage is applied to horizontal amplifier, and then it is applied to the horizontal deflecting plates. So this voltage will move the spot horizontally across the scope screen. Now I am asking what the voltage which is coming out from the time-based generator, which is then amplified by the horizontal amplifier, it is proportional to what, or output voltage depends on what value? Oscilloscope is displaying amplitude versus time curve of a signal, amplitude versus time of the signal. And horizontal voltage, which is the voltage of the time-based generator, it will move the spot horizontally across the screen. So it is proportional to what component?
Time component, mane.
Yes.
Time.
The time-based generator will produce a voltage which is proportional to time. So that is why, depending upon this voltage, the spot on the scope screen will move horizontally across the screen. Because if it moves left and right, then there will be a difference in time. So difference in voltage, difference in time, and we will see later on, time-based generator will produce a voltage which is V proportional to time t. And the the voltage applied to the vertical deflecting plates is proportional to the amplitude of the voltage applied at the input signal, and it will move the spot of light on the screen up and down. That means vertically up and vertically down, and it is proportional to the amplitude of the signal which is presented on the scope screen. So, and inside the cathode ray tube, an electron beam is produced by the electron gun. So, and this electron beam will strike the scope screen, which is made up of phosphor. And when the electron beam strikes the screen, that is why this screen is known as fluorescent screen. and where it strikes the screen, the phosphor will emit, and fluorescent screen is made up of phosphor. And when the electron beam strikes this fluorescent screen, which is made up of phosphor, phosphor will emit a visible light. So the deflection of the electron beam in the vertical direction will be due to the voltage applied to the vertical deflecting plates, and deflection of the beam in the horizontal direction is due to the voltage applied to the horizontal direction. And in this way, again and again, if the beam will scribe the same path, we will get a steady deflection of the input signal on the scope screen. Clear the function of the CRO? But I will go all
Yes, ma'am.
the subsystems one by one. So this is how we can represent a signal on the scope screen. Now the triggered circuit, this is used to, it is activated by the part of the signal, part of the input signal we have seen from the figure, and the triggered circuit is activates the time-based generator, and triggered circuit is used for synchronization of the vertical deflection system and horizontal deflection system, because until and unless both the voltages present on the deflecting plates, we couldn't able to see the image on the scope screen. That is why we need the voltage to be present on the, to display any signal, we need the voltage to be present on the vertical and the horizontal deflecting plates at the same instant of time, and this is known as synchronization of vertical input, vertical deflecting plates and horizontal deflecting plates to obtain a steady deflection of the electron beam on the screen. Do you know the understood the meaning of the synchronization and why we need the voltage at the vertical deflecting plates to be synchronized with the horizontal deflecting plates?
Yes, ma'am.
No,
Yes, ma'am.
Yes, ma'am.
because unless and until we don't have these two voltage, we couldn't able to see the stable image of the signal which we want to display with the help of the CRO.
Yes, ma'am.
That is why we need this. Now, I have already told you the CRO is made up of cathode ray tube, vertical deflection subsystem, horizontal deflection subsystem, and power supplies, because these are the some internal circuitry of the oscilloscope needs a power supply. So these are the power supplies are meant for that. And oscilloscope, this probes is the oscilloscope probe. Now the function or the heart of the oscilloscope is a cathode ray tube. Now from the diagram what we have seen, we have an electron gun and deflection system on one side of the tube or left hand side of the tube, and on the right hand side we have a fluorescent screen. Now the electron beam, the electron gun here, it will produce an electron beam. Now how the electron beam is being produced? When the cathode is being heated, so, and this will emit electrons, and from the figure what we have seen, we have here grid. It is known as intensity control grid, and it is cylindrical in shape with a small aperture along the axis of the electron beam. So when the electron beam comes out from the cathode, it will pass through this grid, and the number of electrons which is coming out from the grid depends upon the voltage applied to this grid. And from the figure what we have seen, this grid kept at a negative potential, and depending upon this voltage, the number of electrons on the beam will depend upon, and it will control. Higher the number of electrons, higher will be the intensity of the electron beam. So by this grid is known as intensity control grid, and there is a knob on the front panel of the oscilloscope, and that knob, if we vary the knob, have you didn't use CRO so far, no? Hello, have you seen CRO or have you used it?
Yes, ma'am.
You have used. So have you seen the focus knob on the front panel of the CRO?
Yes, ma'am. Yes, ma'am.
Yes, sure.
Yes, ma'am. In second semester, we have in our lab.
You are now second year, second semester. How could you perform
Yes, ma'am.
lab?
Ma'am,
In first year, first semester, you have done lab on CRO.
No, ma'am. One.
ম্যাম আমাদের ম্যাম যে
Yes.
ফার্স্ট ইয়ার সেকেন্ড সেমিস্টারে এটা ছিল, মানে জাস্ট ওখানে
Oh,
ম্যাম
you have done a lab by using CRO.
Yes,
Which
ma'am.
lab you have performed?
Yes.
Where CRO is needed?
ইলেকট্রনিক্সে ম্যাডাম, মানে ফার্স্টের একটা ওখানে জাস্ট হচ্ছে ওয়েব ফর্মের ওই
মানে টাইম পিরিয়ড ফ্রিকোয়েন্সি এইসব
হ্যাঁ 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 ওই পার্ট গুলোই ছিল।
In electronics
Waveform-এর
lab.
analysis.
আচ্ছা, ইলেকট্রনিক্স ল্যাবে ছিল সেগুলো। সেখানে CRO-টা
Yes,
ইউজ
ma'am.
করেছো।
ইয়েস
তা
ম্যাম।
সেখানে নবগুলো খেয়াল করেছিলে?
হ্যাঁ হ্যাঁ ওই ভার্টিক্যাল, হরাইজন্টাল আরো ছিল।
So this is the voltage which controls the voltage applied
ma'am,
to
ওখানে হচ্ছে ওই প্রোবের মধ্যে যে গ্রাউন্ড ক্লিপটা, ওই পার্টটা ছিল না। ওই প্রোবে যে ওই গ্রাউন্ড ক্লিপের পার্টটা যেটা
গ্রাউন্ড অসিলোস্কোপের গ্রাউন্ড দেখোনি? ভার্টিক্যাল ইনপুট টার্মিনাল, হরাইজন্টাল ইনপুট টার্মিনাল, ওখানে একটা গ্রাউন্ড টার্মিনাল আছে।
ওই প্রোব থেকে একটা যে গ্রাউন্ড ক্লিপ বলে
সেটা ওখানে লাগানো হয়, সেটা না লাগালে তো হবে না।
ম্যাম মানে কানেকশন গুলো আমরা ঠিকঠাক মানে দেখিনি, মানে আমরা তখন ওই স্ক্রিনে জাস্ট ওই
সেটা নিজেরা ভুল করেছো, এটা তো দেখতে হবে।
বাট প্রোবটা যেটা ছিল সেটার মধ্যে ম্যাডাম যে গ্রাউন্ড ক্লিপে এরকম কোনো কানেকশন
অনেক সময় এটা এখানে আলাদা করে দেখানো হয়েছে। অনেক সময় এই পিনটার মধ্যেই গ্রাউন্ডটা থাকে, ওইটা একসঙ্গে কানেক্টেড হয়ে যায়।
ওকে ওকে
অনেক সময় আলাদা করে ক্লিপ এটা নাও থাকতে পারে আর কি।
আচ্ছা আচ্ছা আচ্ছা, এটা ছিল
অনেক
না।
সময় এইটার মধ্যেই হয়তো তোমাদের ওইটার মধ্যেই ছিল আর কি গ্রাউন্ড পিনটা, সেই
Okay.
কারণে। কিন্তু অসিলোস্কোপ ইনপুট টার্মিনালে অনেক সময় অসিলোস্কোপের ভার্টিক্যাল, হ্যাভ ইউ সিন ক্লিয়ারলি দ্য ভার্টিক্যাল ইনপুট টার্মিনাল, হরাইজন্টাল ইনপুট টার্মিনাল, ওখানে একটা গ্রাউন্ড থাকে কিন্তু সেই
Yes, ma'am. Yes, ma'am.
এখানে যেই গ্রাউন্ডটা থাকবে সেই গ্রাউন্ডের সঙ্গে এই গ্রাউন্ড ক্লিপটা লাগিয়ে দিতে হয়।
ইয়েস ম্যাম দেখেছি।
Now, so this voltage, the voltage applied to this grid is controlled by the knob in front panel of the oscilloscope, and that knob is marked as focus. because it controls the intensity. Oh, sorry, that is marked as intensity, not focus. Focusing এর জন্য আলাদা anodes here. So this is an intensity control knob. Say here, আমি একটা front panel এর ছবি দেখাই তোমাদের. So here, where is the this is the intensity control knob. Say this is the intensity, this is the focus, this is the power supply. এখানে horizontal input terminal আর external input terminal, the horizontal input terminal, then vertical input terminal. কোথায় গেল? This will be the vertical input terminal, horizontal input terminal, and this is the position control knob. And what are the functions of these knobs? I am coming to this now, and also AC, DC, external, internal. This I am coming later on. So this will be the intensity control knob, and this knob is marked as an intensity on the front panel of the oscilloscope. Now then, this beam of electrons, what we have seen from the figure, it passed through the 3 sets of anodes, and these are the pre-accelerating anodes, focusing anode, and accelerating anodes. And all these are also cylindrical. Anodes are cylindrical in shape, and the positive voltage is applied to these anodes. And the function of the focusing anode, it will focus the electron beam, and we have seen these 3 anodes are kept at positive potential with respect to cathode. And the first anode will be at positive potential with respect to cathode, and the second and third anode will kept at higher potential with respect to first anode, and third anode will kept at much higher potential with respect to cathode, and with respect to, that means the voltage of the second anode will be lesser than that of the voltage applied to the third anode. That means the third anode will kept at higher potential than that of first and second anode, and second anode will kept at higher potential than that of the first anode. And all these 3 anodes are kept at potential, positive potential with respect to cathode. And out of this, the first one will be first, and third one will be the accelerating anodes, which accelerates the electron beam. And then we have a focusing anode, which will focus the electron beam. So the voltage applied to this focusing anode, it will, by controlling the voltage applied to the focusing anode, we are controlling the focal length of the electron beam. And this accelerating anodes, it will accelerate the electron beam. So, and electrostatic, generally 2 types of focusing scheme is used: electrostatic focusing and electromagnetic focusing scheme. Though detailed of these 2 principles is not necessary. Electrostatic focusing scheme is used in cathode ray tube, where electromagnetic focusing scheme is used in TV sets. Now, after passing through this focusing and accelerating anodes, the beam will pass through the 2 sets of, from the figure what we have seen, it will pass through the 2 sets of deflecting plates. One set is known as Y plates, and other set is known as X plate. Now, when there is no voltage applied to these 2 plates, the beam will go straight and strikes the fluorescent screen at the center. And when their voltage is being applied, we have seen from the previous figure how the voltage is being applied to the Y plates and X plates. So due to the voltage applied to these plates, the beam will move horizontal and vertical direction. Now, these voltages applied to these two plates is controlled by two knobs on the front panel of the oscilloscope, which is known as position control knob. There will be an X position and there will be a Y position control knob, which controls the voltage applied to these two plates. Now we have seen, that is why here see this voltage vertical position and the amplitude of the vertical signal both controlled by this, and it is marked as X shift and Y shift. এই দুটো knob দেখেছো, which is a Y shift knob is marked as volt per division and X shift knob is marked as time per division. Have you seen?
Yes, ma'am.
দেখেছো? Hello?
হ্যাঁ ম্যাম দেখেছি।
So that is why when there is no voltage in this figure, both vertical and horizontal plates are grounded. So the beam will be at center. When we are going to give positive voltage to the vertical deflecting plates, since the electron beam, it is a negatively charged beam, it will attracted upwards. Since the upper vertical plate is kept at positive and lower vertical plate is kept at 0, and there will be no signal applied to the horizontal deflecting plates, so the beam will be deflected vertically upward. And if the lower vertical plate is kept at positive and the upper one is kept at negative, then the beam will be deflected vertically downwards. Similarly, if this horizontal plate is kept at positive, it will be deflected on the right hand side, and if this plate is kept at positive with respect to this, the beam will be deflected to the left hand side. In this way, beam left and this is beam right. And if the equal voltage is being applied to both vertical and horizontal plate, then what will be the deflection?
0.
Same voltage hole 0.
No ma'am, এক মিনিট।
It will be at an angle 45 degree when two equal voltages are applied to both vertical and horizontal deflecting plates.
Yes ma'am, √2V.
√2V.
Yes.
And the angle will be 45 degree. And if the horizontal voltage is greater than the vertical voltage, whether the angle will be 45 degree or more than 45 degree or less than 45 degree.
It will be less than 45 degree.
Yes, but when the vertical plate will be higher than the horizontal plate voltage,
It will be greater than 45
it
degree.
will be greater than 45 degree. Now there is a knob which it is not on the front panel of the scope, which is known as astigmatism, and it will makes the sharp focus over the entire screen, and the voltage which controls this sharp focus to have a sharp focus on the screen is the voltage applied to the accelerating anodes. That is these voltages, not the focusing anode voltage, accelerating anode voltage. Now the screen, I have told you the screen is coated with a fluorescent material, and when the electron beam strikes the screen, it will emit a spot of visible light. And there is a horizontal and vertical lines scribed on the scope screen, and these horizontal and vertical lines with scales, these are known as graticule. Now come to the vertical deflection system. It consists of from the figure what we have seen, it consists of a coupling switch, then we have an attenuator, and then we have a vertical amplifier, and then we have a delay line. Now what is the function of this coupling switch? Now when here the input signal is being sensed with the help of oscilloscope probe. Now if this coupling selector switch it is placed in, say, DC position, it marked is AC, GND and DC. Now when it is connected to the DC position, then entire signal will be presented on the scope screen. Now if it is a AC-DC superposed signal, then both AC and DC component of the signal will be displayed on the scope of the screen when the input coupling selector switch is connected to position DC. Now when the input coupling selector switch or this coupling switch is connected to AC position, then what we have seen from the figure, we have a capacitor in series. What this capacitor will do?
ওই ডিসি কম্পোনেন্টটা যে থাকবে না, ওর
Yes,
ফ্রিকোয়েন্সি জিরো হয়ে যাবে, ওটার জন্য ওপেন থাকবে।
it will remove the DC component of the signal because capacitor behaves open circuit to DC, because we know the capacitive reactance is inversely proportional to frequency. And since DC the frequency 0, so it will infinite, acts as an open circuit. And when the input coupling selector switch is connected to GND, it will make the horizontal deflection system to be grounded, and it will not make the vertical input terminal of the scope grounded. It will make the horizontal deflection system grounded. It is sometimes used to recenter the electron beam. So here this is a DC-AC superposed signal. At DC position, this is DC coupling and this is AC coupling. We are removing the DC component of this signal. Only AC component is displayed here. Now we have an attenuator. The attenuator, we have a resistor attenuator. We call it an uncompensated attenuator. And the attenuator on the right hand side, we called it to be a compensated attenuator. Now in case of an uncompensated attenuator, the voltage Vs, say this will be the attenuator, the voltage Vs will be Rs divided by Rp by Rs into Vi. But if we are using AC, then this will be in terms of impedance, it will be Zs, Zp plus Zs into Vi, and we know the impedance depends upon the frequency. So if the frequency, but in oscilloscope we need to change the frequency. So when the frequency changes, the impedance also change. So there the Vs, if the impedance change, Vs will also change. But we have but we need Vs should be independent of frequency. That is why we are using compensated attenuator. Now here, this attenuator forms a bridge. Say RP be the one arm of the bridge, CP is another arm of the bridge, RS is other arm of the bridge. Say if this is first, second, third, fourth arm of the bridge, and in between this we have kept a detector. And when the bridge is balanced, there will be no current flowing through this detector. So we will remove the wire AB, and at balance condition, we have RS into XP equals to RP into XS. RP into XCS, RP into XCS and RS into XCP. Clear? When the bridge is balanced?
Yes, ma'am.
Yes.
Because between these two arms we are giving supply. This is one arm of the bridge, this is other arm, this is third, this is fourth, and here we kept a detector.
Yes, ma'am.
So RP into RS into XCP and RP into XCS or RSCS equals to RPCP. And so this will be VS by VS will be equals to RS RP by RS times VI, which is independent of frequency. So the voltage what we get, what will be the output of the attenuator? If it is a uncompensated attenuator, it will change with the input signal frequency, but now in compensated attenuator, it is independent of the input signal frequency. Now amplitude control knob, the input attenuator together with the vertical amplifier is used to change the amplitude of the signal and is expressed in volt per division. So you have seen a volt per division knob and time per division knob, which is marked as X shift and Y shift on the front panel of the oscilloscope. Now next we come to a delay line. Now why we need a delay line in the vertical deflection system of the oscilloscope? Now let's go to the first figure.
মানে যে দুটো যাতে যে সেম টাইমে যায় ওখানে।
Yes, because the signal in the horizontal path, there will be a since this trigger circuit, time-based generator, horizontal amplifier, they are electronic circuitry. So the signal in the horizontal path will be delayed. Now, and the signal, if we don't have a delay line here, the signal will comes directly to the vertical input, vertical deflecting plates. So if there is a signal present at the vertical deflecting plates and there is no, and we have a delayed signal over here, so we couldn't see any signal to be displayed during that interval of time. So to remove that difficulties, we need a delay line to delay the signal in the vertical deflection system, or the signal which pass through the vertical deflection system of the CRO. Now next we have a horizontal deflection system. It is also consists of a horizontal amplifier, time-based generator, trigger circuit, and this horizontal amplifier acts in two ways, internal and external. That means horizontal in internal, when the horizontal amplifier is used internally. Then the horizontal amplifier is used to amplify the signal produced by the time-based generator, and if the horizontal amplifier is used externally, which is marked as EXT on the front panel of the oscilloscope, then this is used to amplify the external signal which is applied to the horizontal input terminal of the oscilloscope. Say here. Now, if it is connected internally, then the signal will sweep trigger circuit, sweep generator, and the sweep generator, it is excited by the part of the signal coming out from the vertical amplifier. This is the internal of the INT knob, function of the INT knob on the front panel of the oscilloscope. And we will see that when the horizontal amplifier is connected to the internal position or marked as INT, then it is used to amplify the voltage generated by the sweep generator or the sweep waveform produced by the sweep generator, which is proportional to time. But when we are going to use external, then this switch will be connected here. This switch will be connected to the horizontal input terminal of the oscilloscope, and this is external. So, and this knob horizontal amplifier is connected to the EXT position. So, it will amplify the whatever be the input voltage applied here, it will amplify that voltage. So this is when internal position, it will oscilloscope will act as an XT mode of operation, and here, sorry, this will be the not XT, YT mode, because amplitude versus time, amplitude is reflected in the Y plate and the time will be in the X plate. So YT mode of operation, and when both sinusoidal signals are being present at the horizontal input and vertical input terminal, then oscilloscope horizontal amplifier will act in XY mode of operation. So if we have both sinusoidal voltages at vertical and horizontal deflection, then we obtain a Lissajous figure. We have a different pattern of Lissajous figures for different different frequency voltages applied to the horizontal and vertical deflecting plates, as well as if the two waveforms has a phase shift between them. This will also shown on the scope screen, and by seeing the display we could able to find out the voltage difference, phase difference between the two voltages applied to the vertical and horizontal deflecting plates, as well as different frequency, the voltages of different frequencies applied to the vertical, applied to the vertical and horizontal deflecting plates of the CRO. And so CRO can be used to measure frequency and phase. I'm coming to that later on. So horizontal amplifier, it works in two ways, either YT mode and XY mode. In YT mode, it will display amplitude versus time curve of a signal, and in XY mode, we will represent one signal versus another signal. Clear how the horizontal amplifier works in YT mode and XY mode?
Yes, ma'am.
And amplitude control, the horizontal amplifier is to change the amplitude of the signal obtained from the time-based generator and is expressed in time per division. And time may be in second, maybe in microsecond or millisecond. Generally, second, millisecond is being given. So this is the time per division knob, and in Y direction, in Y shift, it is volt per division knob. Because we are controlling the amplitude of the voltage, here we are controlling the time of the time or time period of the signal. Now this is the circuit diagram of a time-based generator. The circuit is clearly visible to you. Hello?
Yes, ma'am.
ছবিটা ভালো দেখতে পাচ্ছো? And this will be the sawtooth waveform.
Yes, ma'am. Yes, ma'am. নেক্সটটা ঠিকঠাক দেখতে পাওয়া যাচ্ছে, প্রথমটা ঠিক আছে।
I am coming to the next figure later on. Now here we have, this is a comparator, and this is connected the this positive input terminal of the, this is the power supplies of the CROs, which is here connected with Zener diode here, and the positive input terminal, this is the positive input terminal of the comparator, and this is the negative input terminal. And look at the figure carefully, and from here V0 is the voltage across the positive input terminal of the comparator, as well as this will be the voltage across the different capacitors C1, C2, C3 and so on. And this is the switch which is marked as time per division. If we want to change the time, we will connect different values of capacitor. Now here this time-based generator, how it will produce voltage, this is sawtooth voltage, which is proportional to time, because V0, this output voltage, it is proportional to time. And also time from the expression of time for a particular position of the switch, if this C value is constant and I is constant, because it is depends upon the Zener voltage, Zener diode. The Zener diode has a constant voltage, and this P is the potentiometer, and R is the fixed resistance, and this position and this resistance, these values are known to us, so this current will remain constant. So T0 is proportional to C1 into V0. C1 into V0, which is the output voltage. That is why the output voltage is proportional to time. Now let's see how the output voltage is proportional to time. Now here, when the op-amp supply will be on, then the voltage across the positive input terminal of this comparator, or which is the voltage across the capacitor, say C1, it is 0 volt. And the voltage across the negative input terminal of the capacitor, why it is 0? Because transistor T2 and T3, they are off. That means these two are open circuit. So the voltage across V0 will be 0, or which is the voltage across the positive input terminal of the capacitor. Of the comparator, sorry. Now, at this instant, the voltage across the negative input terminal of the comparator Now, what we have seen, the negative input terminal of the comparator is connected with resistance R2 and 2R2. So it will be, and this is grounded. So the negative input terminal voltage is 2/3 VCC. Clear? Where VCC is the op-amp supply voltage, which is equivalent to
Yes, ma'am.
plus minus 12 volt. Voltage at the positive input terminal of the comparator will be 0, but voltage across the negative input terminal of the comparator will be 2/3 VCC, because R2 plus 2R2 is 3R2, but the
Right.
negative voltage at the negative input terminal will be 2R2 by 3R2 into VCC, which is the op-amp supply voltage. So if we take this to be a 12 volt, it will be 2/3 VCC, that means 8 volt. So the comparator output will be 0. Or comparator, because the negative input terminal is is 8 volt, or which is minus 8 volt, and positive input terminal it is 0. So the comparator output will be low, and transducer T2 and T3 will remain off. Now, the capacitor is charged up with a constant current, and this constant current is driven by this Zener diode VZ, and I will be equals to VZ P plus R. These are, and this potentiometer setting. Now, with this current, the capacitor will charge and the voltage across it will rise. Now, when the voltage across the capacitor will exceed 8 volt, then the comparator output will be high, because
ma'am.
this is kept at 8 volt and this is now greater than 8 volt. So the comparator output will be high.
Already.
And yes, and T2 and T3 on. So it will behave as a short circuit.
Yes, ma'am.
Now, what happens? The capacitor will, at this instant, now when the T2 and T3 will be on, or it is short circuited, then the voltage across negative input terminal will be these 2R2 and R2 by 5. These two resistances are in parallel. With this parallel combination, these R2 are coming in series. So these two parallel combination voltage across these two parallel combination, R2 by 5 and 2R2, this will be the voltage across the negative input terminal of the comparator, and it will be equivalent to, if we take VCC to be 12 volt, it is equivalent to 2 volt. Jodi amra R2 by 5 and 2R2, these two are parallel, this parallel combination is in series with R2, and total resistance divided across these resistance, which is the voltage across the negative input terminal of the comparator, will be R2 by 5 and 2R2. You can calculate this mathematically, and it is equivalent to 2 volt near about. Now, the capacitor,
Yes,
since this is T2 and T3 are short circuited, so the capacitor now discharges through R1. Now, when it will discharge, the voltage across the positive input terminal will be decreasing, and when it is less than 2 volt, the comparator output will again be low, and T2, T3 are off. So in this way, we are going to have a repeated this type of waveform. And we know the charge Q will be C1 into V0, Q is C into V, and Q is again I into T, and I is Vz by P plus R. So T0, it will be C1 V0 by I. So the Shortwave waveform is proportional to time, and it is depends upon, and why we have a different time per division scale, because we have a different values of capacitors here. For different values of capacitors, this time scale will change. So it is marked as time per division knob, and this voltage is proportional to time, and that is why the voltage applied to the horizontal deflecting plates of the CRO will move the CRO spot left and right across the screen. Now clear how the time-based generator is producing sweep waveform which is proportional to time. Clear hoche?
Yes, ma'am.
কে কি শুনছো ভগবান জানে। আর পরীক্ষার
Yes, ma'am.
সময়
Yes.
টুকে টুকে পড়িয়ে মানে নোটসটা পাঠাবো আর সেইটা টুকে উত্তর দিয়ে দেবে, সুতরাং তোমাদের খুব সুবিধে। Now we have a dual trace CRO. Sometimes we need two signals to be presented at the same instant of time on the CRO screen. So for this, now so far if we have a single vertical deflection system and single horizontal deflection system, and we have a single electron gun, we can display one signal at a time only. But sometimes we need to display two signals simultaneously at the same instant of time. That is why we need a dual trace CRO. Now these dual trace CRO are of two types, dual beam CRO and single beam but dual trace CRO. Now in dual beam CRO, we have two electron guns from the figure, what we have seen. We have one electron gun, and here we have another electron gun. This first one is for channel A and second one is for channel B. We are displaying two different input signals, and we have two different vertical deflecting plates, but we have a single horizontal deflecting plates. Now since here we have two electron guns and two sets of vertical deflecting plates, so it will display, though it will display two signals for common time base, but this dual beam CRO we couldn't use because it is costlier, because we have to use here two electron guns and two sets of vertical deflecting plates. Now in case of a single beam dual trace CRO, we have a single electron gun, so that will be less costlier than that of a dual beam CRO. So this is a single beam dual trace CRO. We have here we have two different attenuator and amplifier for two different channels or two different input signals. Then the main here we have a single vertical amplifier and a single horizontal amplifier. Now here electronic switch will connect first channel A and then channel B, and this electronic switch works in two ways. One is alternate mode and another is chop mode. Now let's see in alternate mode how the switch is being connected. Dual phase working mode. So we have alternate mode, we have a chop mode. Now here when the electronic switch, this is an alternate mode of operation. When the electronic switch is in alternate position, the electronic switch will connect vertical channel 1 vertical amplifier for one sweep and the channel 2 vertical amplifier in the next sweep, just like this. Therefore, this is in first it will connect input A, next it will connect input B, and we have two and this is for two different not different, same, but this for first sweep waveform, input A will be shown on the oscilloscope screen, and for the second sweep the second signal will be displayed on the scope screen, and the frequency of this switching is equivalent to the frequency of the signal presented at channel 1 and channel 2. So we have a first signal to be displayed at one sweep, and for the second sweep the next signal will be displayed. So this is two signals at two different instants of time. For the first we have an input A, and for the second we have input B. It doesn't display two signals simultaneously for same instant of time. If we, for a single sweep waveform, if we could display these two signals, then it will be simultaneous reflection of two signals at the same instant of time. So we go for an chop mode. Now here the electronic switch will act as a free running multivibrator. That means the frequency at which the electronic switch connect channel 1 and channel 2, it is independent of the frequency of the signal applied to the channel 1 and channel 2. So at the it will, when the electronic, since it will works as a multivibrator or a free running switch, then it will connect channel 1 and channel 2 simultaneously, and it will take in the first it will take a small segment of channel 1 and then small segment of channel 2 and displayed on the scope screen. So here this is input to channel A, this is input to channel B. So, and we have a single sweep waveform, and we have it will take a segment, first segment from channel 2, here the second segment from the channel 1, then third from channel 2, fourth from fourth segment from channel 1. So small segment of the input signals will display with respect to single sweep waveform in case of a chop mode. Clear? How the signal is being displayed in alternate mode and in chop mode? Hello?
Yes, ma'am.
Here the frequency of the frequency of the electronic switch will much higher than that of the frequency of the signals applied to channel 1 and channel 2. So it will take That is why we call this to be a chop mode. It will take a small segment from 1 and 2 and it will display that during single sweep. ঠিক আছে, আজকে এই পর্যন্ত থাক। Okay, fine. Thank you for listening. I am leaving.
Okay.